Thank you for the invitation. And of course, I'm happy to contribute to honoring John Crossley. Okay, let's move along. My view of logic is very expansive. It's common in logic to study things which are correct in some objective sense. But I think logic is a study of arguments, all kinds of arguments. So one analogy is to economics. In economics, they used to study so-called homo economicus. So there was a simplifying assumption that people are rational and do behave in the best of their interests. And eventually, of course, always it was understood that this was just a simplifying assumption. But lately, more and more evidence is that people do not behave rationally always. And it's actually quite interesting to study how they deviate from rationality. So something like that is in with logic lately. So lately, it was common to study, so to speak, homo logicus, kind of people who are untired, do correct logical derivations, and this fits perfectly mathematical logic, but it doesn't fit many other activities, many other argumentations. So in my view, we should study argumentation for any audience, of course, for the mathematicians, but also physicists, for a jury, for your family, for your government, for the whole humanity, and reasoning of any kind. Not only mathematical reasoning, also legal reasoning, political propaganda, even demagoguery. We don't like demagoguery, but if you have to do it, you better know how to do it. At least, or at least you don't like and you fight demagoguery, you better know the laws of demagoguery. I came to logic because of foundations. Later I'll say a few words about my personal career. And so that was my original motivation. And so that's what prompted this talk in the first place. It would be desirable to do a broad sweep of the glorious past of logic foundations, to examine the less glorious present, and to discuss the future, somewhat uncertain, but time is short and my scholarship is definitely limited. So it will be reduced to a personal perspective and few illustrations instead of systematic exploration of the subject. So the goal is to spur a discussion on the role of foundations. And if you find the talk provocative, you're not wrong. It is intended to be so. I have two epigraphs. One is, actually, I'm not sure, a Chinese proverb. So I had an anonymous referee who said, how do you know it's Chinese? Some people say it's African. So a proverb. So we definitely, foundations allow us to, okay, anyway, you see the point. A less obvious point to people who do pure math is that applications are very important. So here is a quotation from Louis Pasteur. There does not exist a category of science to which one can give the name applied science. There are sciences and applications of sciences, bound together as a tree and the fruit it bears. there is a Russian-speaking, I used to say Russian, but he actually grew up in Ukraine and then moved to Moscow. So now one has to be a little bit more careful. So Russian-speaking, he's known as humorist, but it's really quite a philosopher. So he says it's not enough to know your worth. You still need to be in demand. So let me say a few words about my personal experience with foundations. The first thing that I remember, it was sometimes in middle school. So the teacher was explaining, here are two triangles. We'll show that they are congruent. So let's take a third triangle. And I started to worry, where does she take the third triangle from? So I asked. She obviously was confused. And it was all boys class. All the boys suddenly listened. Not many people listened before that. Suddenly there was complete attention. Everybody looked at her. She turned to me and said, "Shut up." But a lesson I draw is that intuition, this basic mathematical intuition of the mathematical world, is not inborn. You have to learn it. By the way, my question was sincere. I didn't want to make the trouble. It was right after the Second World War. So everything was in short supply in Russia. I stayed in bread lines and other lines. And so it wasn't obvious why there should be infinite supply of triangles. Then I studied at Ural State University and did some work in algebra, but quickly became somewhat disappointed. It was a kind of general algebra. You give me any three Latin letters in some order and there will be a class of group by that name. So it's a kind of field where easy to create well-posed problem, easy to pose problems precisely, which are hard to solve. So I solved one in my master thesis and was quite disappointed. It was difficult construction. And after that, I didn't learn that much. Comparative to the beauty of classical mathematics, that seems kind of waste of time. And at this moment of little crisis, a friend gave me a birthday present, which changed my life. It was the book of Klini, Introduction to Mathematics. And it is the foundational part of it that impressed me. So in fact, if I were in a different country, I probably would go to philosophy, but there was no philosophy in Soviet Union. There was so-called philosophy, dialectical materialism, which is essentially a kind of pseudo-religion, impossible to understand rationally. So then I was this Jewish liberation movement. We succeeded to leave the land of victorious socialism. And on the side, so my parents supported me more than they could, but that wasn't enough for me. So I always supported myself. First, with other guys, we went to railway station and carried things. But eventually a program, and then a group of us, today it would be a startup. We started to work with transportation industry, and I got some taste of it. you do something and then people use it. There is a kind of sweet feeling in that. So when we left, I intended to go to applied things. But when I came to Jerusalem and discovered this Jerusalem Logic seminar, I forgot everything. And for a decade, I spent time in logic, learned modern logic, and collaborated with Shelah and others. But eventually, I wanted to resume my way to applied things. And I applied to zillion of universities and moved to Michigan. It was a rare time that there was nobody to teach theory. So I remember when I arrived and I suggested that I will give a talk, I will want to teach programming. And the chairman says, no, we have enough people to teach programming, you will teach theory. That's why we hired you. I said, but you know, I'm a mathematician. If I need somehow to make a transition. So he considered it and says, okay, you teach programming once. Okay. So there I worked on this problem, what's an algorithm. I better not go there because it's an issue which will be infinite for me. So eventually that attracted attention of Microsoft, and they invited me to start a group on foundations of software engineering. By the way, I said to the guy who invited me, Jim Kajia, his name, I said, Jim, I don't know what software engineering is. And he tells me, nobody does. And that actually was the best time of my life. There was no teaching of people who don't really want to be taught. And you have, in the beginning, it was very difficult because they wanted something. I had this abstract state machines developed in Michigan, and they wanted a tool built on abstract state machines. And it was not easy for a mathematician to create a group and do, but it worked. After that, I got some credit, and my first hire agreed to take over the group, and I was I could move and work on whatever. So I worked with many product groups, usually on whatever they were doing. Because if you do something, then there's a hard task to sell it to people. But if you work on something they're interested in the first place, people appreciate mathematics actually a bit too much. They expect that math will solve more problems than the mathematics is able to solve. In my experience, if problem seems too hard for mathematics, it's probably is in the right way. There's a Russian proverb: if you come to the mountain, don't go over it, go around it. So find engineering solution that's typically works quicker and more realistically. So these are various issues that they work there. So now I want to speak about the glorious past of foundations. And I want to, so obviously, to me, that every science should have logic foundations, but I want to start even deeper with the foundations of human civilization, the first alphabet. So what's an alphabet? It's kind of system of symbols for the basic sounds. It's not obvious that there is a finite many basic sounds. We make a continuum of sounds, and the sounds changes not only from language to language, but from various dialects from the language, from even speakers of the same dialect. Even the same person later on speaks somewhat differently. And yet this continuum of sounds was reduced, actually consonant sounds, because these are the basic sounds of Semitic languages. The vowels play mostly auxiliary role. So this continuum was reduced to few, to be exact, 22. So to me, it seems miraculous that this alphabetic principle was conceived, that it was implemented and was accepted. It's just an astounding idea. And in a sense, a triumph of syntax over semantics, because contrary to pictogram, a word in a given alphabet the word itself doesn't reflect what isn't like what it denotes. It just reflects the sounds we use to of the word. I suspect that making alphabet sacred was probably instrumental to promoting it. So I don't know whether you see, so here is the alphabet. So on the leftmost row, look at the right, the leftmost, this proto-Canaanite, this is the original, these are two parts, 11 sounds and another 11, altogether 22. So this is the earliest. Then Phoenician, here is also Phoenician. Early Hebrew and Phoenician was very essentially the same. Language, from the point of language, they were very close people. The Phoenicians were the outgoing, the traders and explorers. The Jews were at the time a kind of country bumpkins, not on the shore, but more in the mountains and with their sheep, and so on. So this is the modern form of Hebrew alphabet. When you see two letters, one of them is the final letter, because it was too the material on which they wrote was too expensive, so there was no words were written one after another and from right to left. And so the final letters were there sort of to show where the word ends. Similarly, capitals are used in. Let me just say the alphabet is so interesting. You can speak ad infinity to infinity, but let me say that it is the same letters. If you see M is on position 13 in all these alphabets, including English alphabet. So people took a kind of very the order of letters had, for some reason, was given some kind of mystical meaning. So it is in Semitic languages, all of them, Aleph, Bet, Gimel. The third letter is G, Gimel. Then Greeks borrowed, and in Greek you cannot say Aleph because it should finish with S or with vowels. So it became Alpha, Beta, Gamma, but it's G. So the question, how come is in Latin alphabet is C? So in English it's C. Sometimes pronounced C, sometimes Ch, sometimes K. This is Gimel, Gamma, G sounds. And it's a very strong sound, both in Hebrew and in Greek. So this particular riddle, this is all because of Etruscans. So the Romans got their alphabet from Etruscans. Etruscans got it from the Greeks. Greeks got it from the Phoenicians. And Etruscans didn't have the G sound. Instead, they had 3 K sound, K, 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 K. So already in Hebrew, there are 2 K sounds, which became in English K and Q. So here is one of them, Kaf and Kuf. But Phoenicians had 3 K sounds. And then when Romans came, they used just the first one of them, which was K. Now, why they started to write it C, that I don't remember. But they pronounce it K. And so it's Caesar, it's a Circus, Kirkas, or Kirkus. So it was K all along. And it's only when in England, in English, because the French influence, this K started to pronounce C and Ch and all different ways. And when printing one is invented, so I think British printers had to made a decision to use K in many places. So before that, say, king was written C-I-N-G. By the way, what is about G? Where is G? You eliminated G. So what Romans did, they needed G. So they took it C and put a little accent on it, into it, to create this G. Okay, let me leave it. This is from the book by John Mann. From the alphabet's earliest manifestation 4,000 years ago, all other alphabets take their cue. So alphabet was invented once. What is interesting, it's not because it's so perfect. It doesn't fit perfect anything. It doesn't fit perfect. I know Hebrew, so it doesn't fit Hebrew perfectly. But it's good enough. It's engineering, in a sense. But it's also as foundational as it gets. Oops. Now I will speak about something Wilfred Hodges kindly commented on the paper, and he said that they studied the stuff which I will be speaking now. He studied it in Oxford. Now, I didn't study any of it. So in mid-1990s, I was in Amsterdam giving some lecture, and a Russian girl came and said, "Oh, you write those dialogues in Bulletin of European Association for Theoretical Computer Science. You probably fashioned them after Plato." I looked at my face. He said, "Have you read Plato?" I said, "No." And so for the next lecture, she brought me this Theaetetus, and I read and was just overwhelmed. It's an amazing story. So Socrates speaks to two mathematicians, but basically speaks to a younger mathematician, and he asks him, "What's knowledge?" And this Theaetetus says, "I have no idea. I never thought about it." And Socrates says, "Think." So he gave some definition, and Socrates dismisses it. No, think hard. So the guy comes with definition: knowledge is perception. That's interesting. So Socrates thinks about it, criticizes, quotes. For us, it seems like it's the beginning of philosophy. No. Socrates quotes a lot of philosophers and and eventually proves that it's not good enough and pushes this Theaetetus to burst a better definition. And he comes with definition true belief. And Socrates likes it first, then criticizes, and then the young guy comes with a third definition. Knowledge is true belief with an account, and that's the best he produced. And again, Socrates first likes it very much, then criticizes, and at the end he says, "Okay, let's meet tomorrow morning and continue." And that's where we are today, more or less. It's not that people didn't work on what knowledge is. And today we say, instead of account, we have, different expression, but essentially the same thing. But let me move along. Another interesting foundational idea is introduction of variables. So Vieta introduced vowels for unknowns and consonants for constants. Actually, the way he introduced was more sophisticated. They had their own dimensions, physical dimensions, these things. So it's not exactly the way we do today, but it certainly quickly became. Infinitesimal calculus, so you know the story. I tried hard to find portraits of young Newton, and I didn't succeed to find a portrait of young Leibniz. You know, we always see these people in very advanced stage, but sometimes when they were most creative, they probably were not so old. So their work continued quite a bit. Let's see. Well, it seems the same thing. Not sure why it is. There was one interesting story related to calculus. Let me come to the repeat. So which goes from ancient Greece. So the story is that some fellow in Pythagorean school came up with essentially with a proof of irrationality of 2. But that contradicted basic beliefs of Plato, of this people. Not Plato. What was the sum of squares of, if you take a triangle, then hypotenuse, square of hypotenuse is the sum of the squares of, whose theorem it is? Who can speak?
Pythagoras.
Pythagoras, thank you. So the Pythagoreans thought that if you, certainly in such a triangle and much more general, you always have a single small kind of length, and everything else integer multiple of that. And square root didn't fit this modus, this picture. And so this guy, according to a story, possibly apocryphal, was killed for not being sufficiently religious in the proper sense. And so this story was somewhat solved, to an extent was solved by calculus. But because in calculus they have infinitesimals, so maybe there is a kind of smallest infinitesimal, who knows? At least it became sort of vague. But really the story was solved finally by Abraham Robinson in creating non-standard analysis. And so even in non-standard analysis, what you don't have such a simple picture as Pythagoreans wanted, but what you have is that there is an infinitesimal such that takes square root of 2 and 1, and then there are non-standard natural numbers, so you multiply this in, say, infinitesimal alpha. You multiply it by these two non-standard integers, and as a result, you get two approximations to two standard numbers, to 1 and square root of 2. So we more or less understand what really goes on there now. I many times spoke about my standard heroes. I used to speak about Tarski because logicians, Turing, because logicians always, in recursion theory, there was always Church, and I was promoting Turing, but lately Turing became so famous that speaking about Turing, it's just you're drowned in an ocean of voices. And one of my heroes, big heroes, is Kolmogorov. I spoke about many times about him, but this time I want to mention two other names, and these are Hermann Weyl and John von Neumann. And the reason is I'm, in a sense, met them came across their work when I just came to foundations and to logic. So Hermann Weyl was a famous constructivist, and John von Neumann created this alternative approach to set theory, where instead of set, the main notion is a function, which this eventually became Bernays. Bernays eventually presented it in a different way, and it became a Bernays-Gödel set theory. And then, for a long time, I didn't see Hermann Weyl. Now you cannot avoid hearing about John von Neumann because he had his hands in so many things. But last 6-7 years at Microsoft, I was in quantum group, and suddenly I realized that they both are giants of quantum theory. So what's interesting too, this by itself is a huge lecture about Hermann Weyl, but interesting to see how he moved from being constructivist, and he was a student of Hilbert. As he matured, and he was interested in philosophy all his life. Here is a quite fascinating book, Philosophy of Mathematics and Natural Sciences. And here is the epigraph he for his book, one philosopher of mathematics and natural sciences. As we grow older, the world becomes stranger, the patterns more complicated. One interesting thing about Herman Weil, another way I was somewhat engaged with him. Once I was in 1980s in ETH, Zurich, visiting Erwin, sorry, second name escapes me. So the last logician at Zurich, his name will appear, I think. And I see on his table this kind of document in German signed by various famous names. So I asked him, what is this document? And he said it is a bet between Herman Weil and George Poya. And the bet was Herman Weil insisted that in, I think, 20 years, constructivism will win, and certain classical theorems will not consider to be true anymore. He lost that, that bet. As far as John Neumann is concerned, here are the names of collected works of his. Look, just the first volume, Logic, Theory of Sets, and Quantum Mechanics. So they say that when the day John von Neumann died, about 20 people became #1 in their respective fields. Recent past. For a while after Second World War, logic was rather popular and very foundational. Of course, the first computers were designed on logic foundation. Symbolic artificial intelligence dominated for a while. So in AI, logic was huge. Logic programming was quite a fad, partially because of Japanese 5th generation project, non-standard analysis, forcing revolutionized set theory. But then things started to change. While the need for logic foundation, it seems, never was greater, less attention, in my opinion, is given to foundational issues, even in areas like set theory. So the latest kind of result that impressed mathematicians was this independence related to Kolkin's algebra by Elia Farah. It's certainly very, and it's 2006. So of course, set theory is an interesting field. It's very strong people work there, and many of them are very interested in foundations. Nevertheless, I still think that it's less foundational than it used to be. Now, mathematicians are less and less impressed with these philosophers. By and large, logic factions are fizzling at the top math departments. For example, in ETH, Zurich, so they started from Zermelo, Bernays, Stecker, Engeler was the last logician and friend of mine. And I was writing for some very strong Swiss logician. Each time they were, so I think 3 or 4 times when a logician was retiring, I was writing a letter in this guy definitely deserves, but they didn't hire him or didn't hire any other logician. They just were not interested in having logic anymore. In computer science, there are much more room for logicians. So many logicians, especially in Europe, hiding up in computer science departments. But again, the foundational work is not so prevalent. Certainly the golden age of logic in AI is behind us. What about the future? A future may be bleak. Foundational research, foundational logic research may fade away. Significant logic areas may become part of mathematics or computer science. For example, there are very strong people in Oxford working, logicians, model theorists who went to algebraic geometry, but they certainly are big experts in algebraic geometry. So again, let me quote Eliot, T.S. Eliot, between the patterns and the existence, between the essence and the descent, falls the shadow. This is the way the world ends, not with a bang, but a whimper. Now, I hope this will be not the case, that somehow we can reinvent and return to recover the foundational spirit, to make logic research much more comprehensive and make foundation more different foundations of different sciences. So I'm running out of time, so I'll quickly go to a few issues that occur to me. So this is, I think I give this talk for the 3rd time, but when I gave it the first time, I wrote a few issues just that occurred to me at the time. One was inductive inference. It's not deductive, and so it doesn't fall under mathematical logic, but of course it's badly needed. And so when you speak to physicists, and for 6-7 years I spoke to them day in, day out, Popper is very high in their view. They don't take him literally. So there is a critique of Popper, and I mentioned a few things in the paper itself, but they take him pragmatically as a guiding principle. Probably the most influential and successful branch of inductive reference there is Bayesian inference in AI. I mean, there are interesting issues. We speak about information, knowledge, privacy. I mentioned knowledge. We didn't really move much after Plato, but also in other issues. So I was part of a study of privacy. We call it inverse privacy. The basic idea that direct privacy is what other people know about, you. Okay, let me not go there. Well, the important thing when we wrote this paper, I was the one who actually writing the presentation. I realized that there is no foundation of privacy. People disagree what privacy is. And so in this paper, we developed a little bit the beginning of the foundations of privacy just to support our own paper. But I think a lot can be done there. Life sciences. It's an interesting quotation of John von Neumann. If people don't believe that mathematics is simple, it is only because they don't realize how complicated life is. But whatever complicated life is, there are certain aspects of it which can be analyzed logically. So there is this very famous book, Thinking Fast and Slow by Daniel Kahneman, the only psychologist who got Nobel Prize, presumably for economics.
No, there was a psychologist who taught at CMU. Surely you know his name. He also got the Nobel Prize.
Right.
I don't remember his name. You know who I mean.
Yes, I know. So thinking fast and slow, thinking slow is our standard rational thinking. Thinking fast, what we do when, you know, in situations when we have to decide on intuitively. So that mechanism we inherited from reptiles and our old ancestors. And in the book, Kahneman, actually, originally there were two of them, Tversky and Kahneman, investigated this slow fast thinking. And turns out it has its laws. So for example, we deal with probabilities in a very different way. Let's see, suppose you're in savannah and you see something strange. The probability that this is a lion rather than just a tree is very small. But if it is a lion, it's very dangerous. So you run, never mind probability. So and our estimation, the way we estimate probabilities is very much influenced by this. And I think there are room for logic foundational study of slow thinking, of fast thinking. There's a beautiful book by Duncan Watts. I met him, and he also was in Microsoft Research in New York. So the book is called Everything is Obvious Once You Know the Answer. So he started as a physicist and became social scientist, and he has no excuses. You know, sometimes physicists think that, you know, there is no theorems in social sciences. And he says proudly, yes, there are no theorems, but not because we were so stupid, but because it's much more complicated thing. So it's even more involved in life sciences. But again, certain aspects of it can be studied. Let me mention legal reasoning. It's very different. So in a sense, mathematical reasoning is comfortable. You sit in your chair, you have all the time you need, usually, often, you think. Now imagine trying to think when you're in a courtroom and across you there's somebody who tries to argue every point you make, and he shouts, and they have to convince not God, but these 12 people. By the way, the original logic, which became so powerful, logic of correctness, was when in Greece, they went to their piazzas or whatever they call them, and started to try to convince their fellow citizens rather than convince gods. So convincing people This is the beginning of logic, and we certainly should go back there. I want to quote, as I said, Wilfred Hodges kindly looked at my paper on my request, and he noticed that what this expansive view, I didn't discover it. It used to be common. Let me read a paragraph of his. For example, Al-Farabi classified kinds of logic by the practical effects that they were designed to achieve. One kind of logic would attain incontrovertible truth. Another kind was winning people over to your opinions. What looked to us like his inference rules were for him the rules that society had come to agree were good for settling disagreements between two individuals. Thank you.
Thank you very much, Yuri. That was